advancement that they started to build. Like if you have two interferometers, and then you couple the noises, or couple the lasers in the end, then you measure the cross correlation, then you get different noise measurements. So that's one idea. Yes, two independent sources go into two independent interferometers, and then after the beam splitter, you combine them with some phase shift, and then you read out the signal there. In fact, this is not a new technique. They already did this for the holometer, if you heard about that experiment.
So your calculations tells us that there should be some correlations even if there are noises that just...
My computation doesn't say that. My computation is in perturbative quantum gravity. So there, most of the numbers are small. There's one loophole. Yes. So there are some beyond the EFT ideas, and that's what they are trying to measure, basically. I will not go into that much detail. I'm mostly discussing the perturbative calculation, because that is precise. Like you can just develop the full theory, starting from the beginning and the end, and everything comes out. Everything is finite. So the computation is solid there. But some of those results are used in some beyond EFT computations. So I will mention those at the beginning, at the end, but otherwise. So I should shut up.
No.
Okay.
Can we start? Okay, so good afternoon, everyone. Today, we are very glad to have Robin OBERFRANK, who is a PhD student in the quantum gravity group at Parameter Institute. He will talk about geometrical noise in the interferometer. Okay, please.
Yes, thank you very much. Thank you very much for the opportunity to give a talk here. Thank you to LinkedIn for hosting me and all the nice conversations. I'm very much looking forward to the feedback from this kind of audience. It's always nice to talk to people where experimental theory kind of go hand in hand, and there are experts from both sides. So the topic I would like to discuss today is the topic of geometric noise in interferometers. And so most of it is based on this reference, which we wrote with my PhD advisor, Laurent Fredel from Perimeter. And to say at the beginning what I mean by geometric noise, I mean some kind of signature of space-time microstructure. And in fact, this is among one of the oldest quantum gravity phenomenology ideas. It goes back all the way to John Wheeler, where he was thinking about what happens to space-time at the shortest scales. If you try to zoom in, at some point you could expect that the smooth structure of space-time at some point breaks down, and you see some kind of other structure. So imagine this as a kind of space-time foam, where space-time at the lowest, at the shortest scales, has some kind of foamy structure. It looks like a very stormy sea with high waves, and essentially the smooth structure breaks down. And the question is there a way to somehow operationalize and compute something that tells me how exactly can an observable be sensitive to this kind of microstructure? And by interferometers, I'm going to talk about Michelson type interferometers. So these are optical devices. And I'm sure most of you are familiar with the setup, but let's just recap. Let me consider a source of a coherent optical field, like a laser, that goes on some beam splitter, denoted by B, that splits the beam into two. It goes to a mirror on one end, goes to another mirror on the other end. It reflects, goes back to the beam splitter again, and then I have some detector. So this is also how gravitational wave interferometers work. It's a very old technique. So in this case, so as if the length of these interferometers, the arms, changes, then there will be some variations, some fluctuations in the optical output in this interferometer. And for noise measurements, the output that I'm going to consider is the spectral density of length fluctuations. So I'm going to denote this quantity by S, and it has dimensions length squared divided by frequency. So what this means is that as the interferometer arm fluctuates, it changes its length. then I can compute this quantity, I can measure this quantity, which tells me how much of that length fluctuation is localized in a given frequency band. So that is mainly the computation I'm interested in and the quantity I'm interested in. Now, the first problem you could ask me, or maybe you should ask me, is what is the status with the Planck length? So we know that the Planck length is 10 to the minus 35 meters, which is an incredibly small number. So if space-time fluctuations or space-time discreteness shows up at this scale, then how do I exactly imagine this to be observable at an interferometer, a tabletop macroscopic scale? And that would be a very good question. And one intuition you could think of is that if I think of small-scale behaviors in nature, this is not always what happens, is that it gets localized at the short distance scales. One counterexample, for example, is Brownian motion, where you imagine you have a fluid, it has particles, and the fluid particles get kicked at every point in time, and you don't need to be able to resolve those small fluctuations, those small kicks, in order to say that there is a macroscopic effect I can observe, which is diffusion. So I'm going to call this a random walk intuition with a question mark. That question mark is important. We don't know whether this is satisfied by space-time fluctuations, whether we can think of it this way, but it is a nice diagnostic tool we can think of. Now, experimentally, there are some experiments that already trying to measure and characterize the noise. And to give a few examples, there is the holometer, which was in the early 2000s. There is Quest, which is already operating. It is at Cardiff University. And there is one called G-Quest, which is at Caltech. These are all tabletop meter or 10 meters, or holometer was 40 meters, interferometers that are designed to measure and characterize the noise in different kind of variations. And the experimental number that we currently have for this spectral density is 10 to the minus 38 meters squared per hertz. So this is the experimental number of the smallest noise we can measure in an interferometer. And the question is, can we get this somehow from some kind of space-time fluctuation idea? And just as a dimensional argument, so in this case, what we're looking for, you want to compute the power spectral density of the length fluctuations. So let me allow some scaling with the Planck length to some power alpha p. It can also depend on the length of the interferometer with some power alpha L. Can also depend on the frequency with some power alpha omega. And just at the end, let me put a J, which stands for joker. This is any kind of extra thing that might multiply this, because I missed something with this scaling. So that is the diagnostic window I would like to consider for this kind of setup. Any questions for now? Well, the question, yes? Oh, there's a...
Okay, I ask why it is dependent on the frequency.
Well, we don't know if it depends on the frequency. If it doesn't, that just means it's white noise, right? It's a Gaussian noise that you could expect maybe some kind of space-time signature can have some non-Gaussian effect that you could look for in an interferometer. In fact, that's experimentally is maybe one of the main effects you're looking for. What we're measuring now, this is a Gaussian noise. So in this paper, we lay out a precise computation, which is in a framework of perturbative quantum gravity. And let me describe that computation now. So I'm going to consider a simplified model of such an interferometer, and I'm going to compute a time delay of null rays. So in this case, we have a simplified model of an interferometer. Consider we have a space-time diagram here. I again have a beam splitter. This is the word line of the beam splitter. I have a mirror, and the beam splitter emits a null ray, goes to the mirror, comes back, and arrives back to the beam splitter. Now, in this setup, the metric is going to be Minkowski plus linearized perturbations. So Minkowski, if I ask the beam splitter how much did it take for this photon to go out and come back, in Minkowski, the result is 2L, where L is the length of the interferometer, plus some delta tau time delay that I can compute. And this delta tau is going to split into two parts, one for the outgoing null ray and one for the incoming null ray. And this plus minus can be written as an integral of some combinations of the linearized metric perturbations. Yes?
Sorry, when I think about that, with this beam splitter and mirror, they're also quantum objects. So I could also think that they have some uncertainty in position, some lambda, whereas the space-time is classical. Is there any way to distinguish these two things or not?
So there are those kinds of models as well. When you're looking at geodesic deviations between two massive objects, then you're quantizing the mirror and the beam splitter, and you're looking at how much does the length fluctuate. This is an alternative setup where I'm only quantizing the metric. Qualitatively, I think the results are very similar, as long as you're in perturbative approach. So here in this setup, I'm basically writing the time delay that is measured by the beam splitter as a reference frame. It's given by the metric perturbations. And this is the second to last big formula I'm going to write, I promise. Let me write this in spectral representation, d4p to the minus ip x bar, where these are the background geodesics here, times there's a tensor sigma AB contracting the metric variations in momentum space. Now let's understand this first. So this sigma, basically this contraction tells me that this is a Riemannian curvature effect, where in an interferometer, I always have a frame, a two-dimensional frame picked by the interferometer. It tells me what is the future direction, that is t, it's a time-like vector. And there's n, which tells me where the interferometer arm is pointing. And this is a gauge-invariant observable, so it can be explicitly written in terms of the Riemannian tensor, and it is precisely this contraction of the Riemannian that enters. And this sigma AB, it is a representation of that in momentum space. This basically projects the metric component onto the interferometer plane that are relevant for this kind of time delay observable. And this is a fully gauge-invariant observable in the linearized setup, and that shows up as sigma AB, function of p. It annihilates all the longitudinal modes. So that's a consistency check in this case. And if you remember from the previous blackboard, what I'm interested in is the power spectral density. And in this model, I'm going to write it as just the two-point function of the time delay, of the time delays. So it's going to be S of omega. It's again four-dimensional integral delta of omega minus p0. This is the last big formula. So this is a four-dimensional integral again. There is a Dirac delta function that basically tells me what is the frequency that the interferometer measures. So this defines the frequency. It tells me that it is the zeroth component of the momentum. There is this extra function. Let's call it a response function that tells me how different form momentum modes are weighted when I compute these fluctuations. For example, this function will tell me that the modes that are collinear with the interferometer arm have the highest weight. So let's say this experiment really corresponds to me having this laser, pointing it at the wall, and the light comes back and I measure the time delay, and then I measure those correlations. So this tells me that the modes that are exactly collinear with this beam have the highest weight, and as I go away from that collinearity, they have lower and lower weight. And also, as I consider higher and higher frequency modes, they are also damped by this response function. This is purely a geometrical effect. It comes from these geodesics, basically. And then the most important part is this two-point function. This h sigma is just this contraction for shorthand. So this is the two-point function of the metric correlators, and that is the main ingredient in this model. So these are the geometric fluctuations. And I want to emphasize that in this case, basically, I haven't assumed what these metric variables are doing. This is a completely off-shell computation. So you can treat it as a general framework where you have to tell me what is the dynamics of the metric perturbations, 1. 2, what is the state rho that I want to compute? So these are the two ingredients. Oops, let me. So this is the main. So what I need, dynamics of H plus the state rho. So those are the two main ingredients. And now I'm going to consider examples. The first one would be the intrinsic fluctuations. Now, what do I mean by intrinsic fluctuations? I mean that there are no matter fields. We are completely in vacuum. And in that case, you're just solving the homogeneous wave equation. And these are also the transverse traceless modes. So in this case, you have a vacuum state. And then what you need to compute is precisely this metric correlator. And it's going to have the form, it scales with the Planck length squared. There is, yes. There is the canonical normalization of this field. It's imposed by the commutation relations.
And it says that LP has to be being exactly in the units as it is?
Yes.
As a numerical way? This will be remarkable. You can derive the constant.
No, it comes out numerically even. If you want to impose this tells you that you need, it is a Planck length, precisely. Yes, I mean, this implies that the action is like 1/16 pi g Newton, da da da.
Right? And then how should I combine these constants? I mean, to just get LP and not 10 times LP? Or, like, I'm really puzzled with the... Okay. Sorry?
Is this just saying that one graviton has one Planck length?
In the end, I wouldn't say that, no. It has something to do with...
H bar, right? And it says the quanta has each mode of this H.
Yes?
And it does just one Planck length at certain distance.
I would be a bit careful with that. So what's definitely true is that in this picture, the Planck length doesn't look like the scale of anything. It is really just a normalization constant. So a priori, it's really not a scale of anything. Once I will compute this in a few moments, then you will see that it's actually the scale of these shortest fluctuations that you can consider.
It's very similar to this Dyson graviton. I mean, this is my question or statement.
Yes, I think it, yeah, yeah. But in this case,
The graviton has h bar omega energy. This automatically gives you Planck length.
that one graviton gives you a Planck length worth of Planck's fluctuations. Yeah, yes. In fact, if you want, this is the precise computation of that argument. I would say that it's the other way, yes. But indeed, here the Planck length, it's a normalization constant. You could think of it from the action point of view. If you want to do a path integral, then the Planck length is just saying, I want to normalize it to 1. So that's that statement. But then there's nothing else that I could...
I want to understand wherever LP comes, I multiply and divide by 2. And then I say, okay, now it's still normalized.
Yes?
But I have no meaning to distinguish why LP is important, not 2LP. I mean, I don't understand it. It's on my part,
Mm-hmm.
it's my ignorance.
Yes, no, I agree. Like if you want to set the Planck length from the path integral point of view, like you want some...
I understand that when you compute something, it can be LP times whatever you, I mean, on the other side, it can be 1 over LP, such that it cancels it. So I understand this.
you want to multiply and divide.
Does it mean anything that this is the minimal length or whatever the characteristic fluctuation scale?
At the dynamical level, I agree. But once I compute the spectrum, then that number is going to enter. So let me write that down, and maybe that's going to be a more precise discussion. So there is Planck length squared coming from here, and the gravitons are on shell, so there's a delta of p squared. These are massless modes. And then once I compute the power spectrum for this vacuum state, I get Planck length squared times the length of the interferometer times the dimensionless function of the frequency times the length. And this function, let me do a plot of this. So here I'm plotting S divided by L Planck squared L. So this is dimensionless. And then I'm plotting frequency times L. So this function starts off at 0, goes up, and starts oscillating faster. This is a log-log scale. And then it goes down as omega L to the minus 1. So this computation was first done not that long ago, actually. It was Carney and collaborators in 24. And if you plug in the numbers, so first of all, there's a maximum here. Maybe that's important.
What is the name of the paper?
Sorry?
What is the name of the
The title of the paper? Response of interferometers to the vacuum of gravitons, something along those lines. Yes, Daniel Carney. Yes, yes. So there's a maximum around when the frequency times the length is at the order of 1. It's close to 1. So that means given an interferometer of length L, there is a maximum at different frequencies, depending on that length. And then it falls off for large frequencies, and it starts off at 0 frequencies. Now, if you plug in the numbers, what is this? What is this height? The maximum, we're going to get 10 to the minus 78 meters squared per hertz. What do we compare this with? 10 to the minus 78, 10 to the minus 38, haha, too small.
What's the intuition that it's almost like linear growth to the maximum? I never heard that.
It's just the wavelength of the graviton. When a graviton is much longer than your interferometer, like the gravitational waves, you only have a reduced sensitivity, right? The wavelength of the graviton is just the length of the interferometer you get pulled, and then it oscillates, right? So if you make the interferometer longer, then you have more periods of the graviton wavelength, and so it has this characteristic fall off.
Yes. It's some kind of confinement effect within, yes. So coming back to the question about the Planck lengths. So if you normalize that way, as I said, we did using the commutator, pi h I h bar. So you impose this. This fixes the canonical normalization of the field h. that tells you that this must be Planck scale. And dimensionally, you can say, okay, this is a power spectral density. Okay, what can I mean by length fluctuations? Let's call them delta L. That would be the integral of the spectrum d omega for some kind of range, square root, this to the, 1/2. And this will be proportional to Planck length. So this is the statement that in this case, we only have the vacuum gravitons. So there are actually no gravitons in this case. It's only the vacuum state. In that case, these length fluctuations are set by the Planck scale. At least the overall scale. These numbers are like 10 to the minus 3. Oh, the height of this maximum. This is the dimensionless number, right? Curve. So this function that can compute it exactly how it looks like. It's an analytic function of sines and cosines and rational powers. And this maximum tends to have this value. In why is it so low? It's a computation. Otherwise, I don't know.
Does it have something to do with 3 dimensions and the geometry is not ideal?
Three-dimensional geometry is not ideal in what sense?
You said something about geometric factors, right? So where the P points.
Sorry, geometric factors. Where?
This 10 to minus 3. So if I would have just 1 dimension, wouldn't you expect it to be 1?
Ah, I don't know. But in one dimensions, I can't even. Yeah, gravity is trivial. I cannot have gravitons. So that's. But as a toy model, I don't know if it would be one. That's. Yeah. Yeah. What I can claim is that this is an exact integral. It's given by this formula. You plug it in, you can evaluate it, and that's what comes out. I don't have a deeper interpretation of why exactly 10 to the minus 3. The next case, it will be a bit lower, and that's a similar computation. Just angular averages and this kind of, there's lots of integrals to evaluate, but in the end you get a maximum, and that is a number. So this was for the vacuum, and now you might wonder, S is dimension full, the curve that I'm plotting here is dimensionless. Omega L is dimensionless, S over LPL is dimensionless. In natural units, S is length cube. So that's. Okay, now you wonder what is the state dependence? So next, let's look at the thermal state. So by thermal state, I mean there's a density matrix, e to the minus beta h over z. Then you can compute a power spectrum similar way. Let's call it S beta. You'll find that approximately it is the same as the vacuum. Omega times the Bose-Einstein distribution factor, which is beta omega minus 1. So in this case, it's not the graviton vacuum. There are gravitons in the universe, and they are thermalized at some temperature beta. They have a thermal distribution, and this is the noise that you compute. Now, why is this interesting? I had blue somewhere here. Let's plot it on the same curve. So this was the vacuum, and now we plot the thermal case by blue. For large frequencies, it looks very similar, except that for low frequencies, there is a plateau, and it has a finite value. And this finite value scales as L over beta. So here we have a new scale. Now, if you remember, in the beginning, Visibility of the fringes in what? This becomes enhanced. This is always greater than the vacuum. That I can claim, but it contradicts with some intuition.
Because it's a mixed state. That's why I'm saying that whatever the effects you feel, associated to pure state, you feel like you will lose this.
Uh-huh.
And this is an interesting effect, isn't it? Kind of
Yes.
oscillating thing. But
So this
because then if you say, well, it increases its sense, then I can replace all the theory and say, oh, it's thermal noise. It's not anything about gravity.
well, but this is not the same kind of thermal noise because this is a specific frequency characteristics, right? So this is thermalized gravitons measured by putting a photon through this space-time. That
Expect by analogy, no really, that if you make infinite temperature limit, you don't have any effect.
infinite temperature limit, you would expect that.
You don't have an effect, usually, if it's extremely state is then totally mixed state. So
If you take
noise is a very white noise, like no effect.
if you take infinite temperature limit, this spectrum blows up. This gets stronger.
It gets stronger but flatter. Somehow there is no effect. And that's why
If you,
it should be flatter, but you minimize so reduce it.
you would yeah, you would converge to this curve, yes. You would get this flat curve, yes.
And both frequencies.
No, that's true. Yes, I agree. But then, whether you want to say that as disappearing
So
or
what he says that if your effect is to resolve these minima and maxima, and they get the distance between them gets smaller with increased temperature, then it will be harder.
as you're saying, this specific signature that would show the graviton effect, that would disappear for the large frequency. Yes. Yes, yes, yes. That's true. Large temperature, yes, yes. I agree, yes. But one point I wanted to make about this plateau is that if you remember in the beginning, I was talking about this random walk intuition, whether this is true for space-time, and turns out that the signature, this plateau is exactly the signature of that random walk intuition, or some form of that random walk intuition. So first point for the thermal state, there is an enhancement. This is always larger. And second, this random walk. Now, what do I mean exactly by that? So completely aside from this, what is a random walk? I have a particle that is bouncing around, and every point in time it has some instantaneous velocity. So, yes? Inverse temperature. If this goes, if temperature goes to infinity, then this blows up. Yes, 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 yes. Is it okay? Or yes. So for this random walk, let's consider it just a toy model. I want to write down the displacement of this particle as integral from 0 to t of the stochastic velocity field. Then I can claim that for large time, if I compute the mean squared fluctuations, this is going to scale like t times velocity correlator at 0 frequency. So this is the standard Brownian motion argument. The longer the particle evolves, the further away it is. This is just a toy model, but it turns out you can match this computation to this, where t becomes the length of the interferometer. Omega equals 0 becomes the condition p dot l plus and minus, either plus or minus is 0, where, let me use different color, is l plus, these are just the null vectors. And this v squared, correlator is related to this function that keeps appearing, trace sigma squared, which is, morally speaking, p dot l plus squared, p dot l minus squared. Now, why am I writing all this? So this condition means, in the Brownian motion picture, that the Brownian accumulation is a low-frequency effect. It is an IR effect. And the analog of that for the interferometer case is that I'm looking at modes of the fluctuation that are, again, collinear with the null ray. That is when p dot l plus or p dot l minus is 0. So those are the accumulating modes. Those are the accumulating modes, except that when I compute the correlator, there is this extra factor coming in, which is purely coming from the Riemannian contraction. And when I need this condition, but for that, in that case, this factor is always 0. Yes.
Now I understand, but this accumulative effect, like I start a random walk, then I don't start the next one from the previous position, but where I stopped previously, and then I go.
Yes?
And that accumulates, and I see this kind of extending region of fluctuation. But this goes on repeating this process many times. So what is here repeating this process many times?
Yes, maybe the conceptually different part here is that that is a repetition in time, whereas here the Brownian accumulation is in length. So that, I think of that differently.
So what would be the effect? I mean, I understand. You said once you're back, there is some fluctuation, okay? I can understand.
The effect would be that the longer the photon travels in the space-time, the stronger the time delay effect.
So you want to extend L?
Yes. In that case.
We already have a computation for any L. Now you're adding a new phenomenon.
No, I'm not adding it. I'm observing it.
Then this should already follow from that. If I put now 2L, I should get the correct result.
No, because this is the vacuum computation. And for vacuum computation, you do not get this accumulation precisely because of this factor. In fact, this factor is universal. You see it here. You also see it in the thermal case. The reason why you get an accumulation in a thermal case is because the Bose-Einstein distribution factor blows up for 0 frequency.
So can I just so you could then perform equivalent calculation without having analogy to the random walk for different L's, but the way how to understand this result is through the random walk, or it's two different calculations?
These are two different. So only thing I'm
talking about thermal.
yes, only thing I'm doing plugging into this formula with different states. This random walk is an intuition that you can work out that essentially this computation looks the same as this. This is the dictionary. I'm not adding anything into it. It is pure, straightforward thermal state computation of this formula. So the bottom line is, for a thermal state, this random walk intuition is satisfied. The longer the path the photon travels, the stronger this power spectrum that I measure. If you plug in the numbers, for interferometer, it's still small. That doesn't help restoring this number up all the way to the interferometer scale, but at least there is an effect.
But I mean, what you say is right, it's the same as what if you're on 3, right?
So in the thermal case, this would be larger, depending on.
The green one, or what color is this? The green curve, right?
Yes.
This is the same one as the random walk.
Same one. So yes, I wanted to. No, if I so the thermal is the blue, and this
The same as the random walk.
yes, and it continues. It starts basically. Then it starts merging. So this is how the curve looks like.
This is the same thing as the random walk.
The blue curve.
Yeah.
Yes. The main effect is that at 0 frequency, it has a non-zero value, which scales with the length and the temperature. Whereas for the vacuum case, it goes to 0. That is precisely this cancellation effect. So this factor is universal. So it's more like, by the design of the observable, it doesn't want to accumulate unless you have a state that introduces a new scale, which is the temperature in this case, and that is why you can have this accumulation. So there is a state-dependent effect. Otherwise, somehow there's some underlying basic geometric reason to why these modes that would accumulate, they are just annihilated by the way you have to contract the Riemann tensor. So that is a kind of mysterious effect. I'm not sure I understand fully why exactly that is the case, but that is the case. Now, one last state. I just need to squeeze it here. Sorry? For any vacuum, what other vacuum would you consider? This factor, yes. This factor vanishes. This is state dependent. This is gauge invariance, if you want. Because the sigma annihilates all the p modes, and in this correlator you have, let's say, the transverse traceless projector. Once you contract it with sigma, all the p modes vanish. And essentially the only thing, by symmetry, the only thing you can have is a trace of this tensor squared. And that is enough to annihilate all the accumulating modes. Unless there's a state-dependent divergence in this case, which is why it's restored. Does that answer the question?
There is no that effect in the vacuum.
There is no.
This effect, there is no.
There's no accumulation in the vacuum. No, the vacuum is just this curve.
Why it's strange for me is that I always consider thermal normality as something which decreases the quantum effect. Somehow maybe there is a very strange effect that maybe it does a decrease, but at the end prolongs this accumulating quantum walk, which is
And by
counterintuitive.
the decrease, do you mean that
I think
the
it decreases in the sense that maybe this is smaller, because if it comes in the t goes to infinity to flat, that means that it decreases the fluctuation, decreases. But maybe you're talking about something where you gain, nevertheless, through this accumulation, which seems strange.
But do you mean that the possibility to distinguish the quantum from the classical fluctuation? Or really you would expect that for large temperature, this just disappears?
I expect that this disappears, but I'm not saying that it's. You want to say us, in a sense, that it is interesting that thermal state can provide you something positive in the sense that easier to detect quantum fluctuations of the space-time.
Yes.
Right? Good. And and then I would say this is counterintuitive, because if you have a pure state of the space-time, like a vacuum, which will be the strongest quantum fluctuations, everything else when you mix, you can incoherently mix, you can only cancel interference effect and so on. Nevertheless, I'm not saying it's not like that, because you might have a decrease of the quantum features, which I would say is the minima maxima, a little bit, but somehow you gain because you somehow observe it over the longer times and this accumulate, and this you cannot do it in the vacuum, which is, I don't fully understand, but
I see, yes.
Isn't similar to Casimir? Casimir also vacuum fluctuation. I mean, you can interpret as vacuum fluctuation and then actually increase it with temperature.
yeah, but this is just thermal. If I would have any measure about the difference between thermal and quantum fluctuation, I think it would decrease. That's my opinion, but maybe I'm wrong. And,
The way I think, the way I think,
quantum fluctuations, say, well, look, I discovered something. I say, yeah, thermal fluctuations, who cares?
the way I think about it is that this n beta basically counts the gravitons. So this is expectation value of A dagger A, right? So if I increase the temperature, there are more gravitons. That's my intuition.
If you have a harmonic oscillator increase, there is more, excitations, but they are just random excitations from the purely random state. I mean, thermal, always random. So if you come and say, I observe something, I would say, well, I can cook a soup and observe the same, so it's not, you know what I mean? So you do have
see.
contain something.
I see. I see. Hmm. Okay, let me move on to the next states. I just need to squeeze it here. Given the name, this is the squeezed state. How do I squeezed state? So for squeezing, basically what I have, squeezing is parameterized by a complex function which has a magnitude and a phase. These all depend on the frequency. And the way you think of squeezing is that, let's consider you have the graviton vacuum state, and you squeeze it. You act on it with an operator, and what that does is that it creates gravitons that are entangled. Let's say it creates a graviton that goes in momentum direction p, and another one which goes into one direction minus p, and then you go through all kinds of momentum depending on this function, and you create that kind of state. You get a very similar effect to the thermal case in a sense that the function, this is called zeta, is basically the same as the vacuum times e to the 2r of omega. So it's similar in the sense that, again, you have an enhancement similar to the thermal state. It's because of the number of gravitons. Basically, I have a bunch of gravitons created from the vacuum. Then they increase the signal. And this is given by a general function of the squeezing strength that is a function of omega. Now you might ask, how do I think of this squeezing? Because this is just kinematics. I can choose whatever state I want. So is there some kind of realistic squeezing of gravitons that you can think of? The answer is yes. That is the cosmological expansion of the universe. So as the universe expands, you can do this simple computation. You have a field theory. You put it on an expanding background. Then you're going to see that the time evolution, the Hamiltonian of this object, purely because of the expansion of the background, has a squeezing effect. So the same thing happens for gravitons. And then there's a computation to do whether, given the history of the universe, the kind of squeezing that is suffered by the graviton vacuum, is that enough for this kind of experiment or not? So I don't have an answer to that right now. So that is the squeezing. Any questions related to this? The graviton vacuum. So you take this vacuum state.
But maybe in this pi and h, there are two kind of observables. You can squeeze state, you can usually squeeze in one, we say quadrature in couple of cases.
Ah,
So you can squeeze in h, but maybe extend it in the pi or the other way around. So, I mean, if you measure the position, I would say something like squeezing position would be better, but I don't know.
so the squeezing I consider here is that there's the vacuum and there's some exponential function acting on it. Which squeezing quadrature does this correspond to? Or it depends on these functions? Maybe that's what you're referring to.
Yeah, I mean, basically you get either r omega or 1 over r omega. Because at the end you have to,
Uh-huh.
I mean, satisfy Heisenberg answer relation. So if you squeeze somewhere, you have to.
Right.
So I guess the question is, if you want to enhance the floor, this r omega should be very large.
Yes.
Okay.
Yes, yes. It blows up as e to the 2r. In fact, you need a squeezing strength at the order of 50 to match the measured value. But cosmology would give you a specific, like you can compute r and theta from cosmology. Interesting thing, theta doesn't contribute. So it's only the magnitude. So that cancels or vanishes.
What if between the B and M, I put a strong gravitational field, like even extreme case, a black hole, and your light pass just right outside the horizon, and from the blue shift and then red shift. Would you have a cumulative effect? Would this kind of allow you to reach higher energy?
That is a great question. I don't know the answer, but I wanted to figure out something like that. Like how do the quantum fluctuations of black holes affect this kind of, yes.
And also related question, what if I put a tiny black hole, super hot, like because it goes inverse with the mass, and will that
Like a quantum object, or
very, very small black hole.
So when I put a small particle, but in what sense is it a black hole? You're saying it's a small black hole?
A small black hole. That's why then you can be super hot. Then you
Because of
particle.
Hawking radiation?
Yes.
Yes?
Yeah. And then you have a thermal state that's naturally in a very high temperature. Whether that can help increase the effect.
Ah, I see. Interesting.
This is I cannot set up experiment.
No, these are great questions. I don't know the answer now, but I think these are great questions. Thank you. In fact, yeah, doing these computations in different backgrounds and see how these fluctuations are enhanced. Like, what happens if I send a photon and it goes around the black hole?
Yes.
Does it pick up some extra fluctuations because of that black hole? Because we do measure these photon rings, right?
Yeah.
From EHD. So what happens if I do the same calculation, just photon going around the black hole, and we do measure those, and we also have timing data for them.
And also for the gravitational lensing from a distant star, if it gets distorted by the black hole, there's kind of there's a measurement of we know how far the star is and whether some of the.
Yes, very good. Yes.
So I have a fundamental question. Like whatever you put it and treat it classically, it will be a classical background. If you want to go to see how is fluctuation around the classical background.
Yes, around the horizon.
So like I think it's very good to follow up. I'm just lacking the intuition why it would help. Because whatever I mean, put it, it would be some classical background. And then this is what I don't want.
You don't want classical backgrounds.
I don't want to detect this. So I want to go beyond that.
Yes, but that part is this eta. It's like, for instance, you can give a black hole geometry, but you still have fluctuation on top. You still have quantum gravity effect.
No, I understand. And they are touched by H.
Yeah.
An alternative effect would be, I don't know how to do that, is here we are quantizing perturbations around the classical background. And what if I find a way where I can quantize the background itself, like in cosmology, some either mini superspace calculation or something where, can I do something similar there? Where the entire space-time is quantized. What happens?
So you can put a large mass next to B in a superposition. Yeah, I mean, sure you can.
Yes.
You can make it something which is not linear. I mean,
But even then, the metric is Minkowski plus perturbation, but the perturbation is created by the masses.
yeah, and you can then not be constrained to. Because what is the fluctuation? Fluctuation is the second, whatever. What I want to say is you are not bounded on Planck length anymore because you can scale your mass as you wish. You put a black hole in a superposition maybe close to B or far away. And then you would have a non-well-defined space-time in which fluctuation will be far larger. But this will not answer your initial question. You want what is the fluctuation of your almost classical space-time?
Well, yeah. Yes.
But if you just want the effect, I think they are certainly better and easier way.
Uh-huh.
I mean, I don't know whether it's easy way, but once the people manage to make a massive superposition, maybe.
Now, for me, understanding what are ways to make these numbers bigger would be very interesting. Even though, I mean, initially I started from, I have some basic space-time, flat space-time, and I have fluctuations around that. How big are those? So I can compute them. They are small. But if there are techniques, realistic techniques that make these fluctuations bigger, that would be interesting. So maybe that goes to the next topic, actually, where I'm not in vacuum anymore. I have a stress tensor. So these are what we call induced fluctuations. And by induced fluctuations, I exactly mean that there is a non-zero stress tensor. So my metric, let's call it capital HAB now, is sourced by the stress tensor of some field, of some matter field. And to solve this equation, you need to, or one way to solve this equation is to have separation between a system and an environment. So basically say that the metric perturbations are the system, and I treat the fluctuations of the matter field as an environment. And then you can write this metric as just a convolution with the Green's function of this operator. You're convolving it with the stress tensor that needs to be in normal ordered. So that is an important point. If you don't normal order, obviously you get the usual problem. This is the cosmological constant problem. You get an infinity that normal ordering is a way to regularize it. But one thing to think about is, if I normalize it in a different way, would that somehow affect the interferometer observable? Because that is an infinity that we drop basically for quantum field theory computations, let's say scattering experiments or these kinds of things. But this is a different kind of observable. So I'm asking whether that extra factor, the extra large numbers that come from this that I can't treat in any way, would affect somehow this interferometer observable. I'm not going to answer that today. I just... Yes, this is just a matter field, yes. In fact, first, let me just take a massless scalar field. And then, again, I need to compute this function, the two-point function. We will have a similar form, 8 squared sigma. Now I have Planck length to the fourth, because there's a g Newton appearing here. I have the same function as before, trace of sigma squared. Then, so these are not gravitons anymore. Remember, for the graviton, we had on-shell fluctuations. These are delta p squared. Now we have a theta minus p squared. So instead of being on the light cone, we are inside the light cone. It's a three-dimensional space. And the reason why that is the case is because the stress energy fluctuations, which I'm considering here, have a stronger UV divergence. They have a stronger short distance singularity, and that number enters into the dimension of the support of that function. If I compute the power spectrum for a zero mass particle, going to get L Planck to the fourth divided by L times another dimensionless function, which I again can plot here. Very similar to that one, starts off at 0, except that it starts increasing instead of decreasing. It decreases as omega L. And that is, again, the same effect about the short distance singularity of the two-point function. That is why it increases instead of decreasing it, as in this case. But because of the Planck length to the fourth, this is even smaller. I don't even want to write down that number. But it's interesting that if I have a matter field, as its stress energy fluctuates and it backreacts on the geometry, that effect is somehow much, much smaller than the graviton baseline computation, which doesn't need any stress energy in the space-time. Somehow it seems to be much, much smaller.
That's like the backreaction from the fluctuation of the stress energy.
Yes,
So yes,
and it's the vacuum. And it's the vacuum state, so maybe that's important. This is the vacuum state of the matter field. And now what you said about black hole and putting large masses, that would change the computation right there.
or probably not a black hole, just a usual nanoparticle there.
Yes.
Then you still have like the ground state, but it's not a usual vacuum. It's a shifted vacuum.
Yes, yes, yes.
In that case, you would have, so then that's not the stress energy tensor backreaction. That's not the fluctuations backreaction. It's the irregular stress energy tensors induced.
Yes, yes.
Try to enhance or do that.
You're asking? Or? I would expect enhanced, definitely, but the main technical problem is that that changes the background. So you need to do the whole computation on a different background. You need to solve the quantum field theory on that background. I think conceptually it's definitely interesting, and that's where I would want to go. Technically, it's more complicated.
The fluctuation of the macrostress energy tensor backreaction create the graviton fluctuation. That's why the order is small.
Okay, and how can I distinguish what is the gravitational field sourced by the matter field? And
That will be T00. This is not the fluctuation of the T.
Okay.
That's the leading order, like this. Again, for His calculation, you also do not have to change eta. You can also put the stress energy tensor and create H. Yeah, but we can discuss.
Well, that could be, isn't that unstable? Isn't that unstable if I don't change eta? Like if I have non-trivial stress energy, I have matter fields which will create gravitational fields, and if I don't perturb around the gravitational field, the classical background created by them, then Minkowski should be unstable, no?
I think that's the assumption that the matter field is not so strong to change your Minkowski yet, but it has non-trivial.
Ah, I see.
Why should we, if it's a static, why should we go unstable? Even if it's change the Minkowski, why should it be unstable?
Well, the Minkowski starting point would be unstable, I think, because then you have a stress energy in a space-time that doesn't solve the first-order Einstein equations.
Why should it be unstable even if it doesn't solve?
Because it's going to push away the background, right? So
There is no well-defined background then.
okay, I guess that's another way to say it, no?
But it's not unstable. It could be a stable configuration. I mean, I don't know what you mean unstable. I thought you want to say something like decoherent or something like that.
No, I just meant the simple intuition that once I have a stress energy in a space-time, that doesn't solve the vacuum Einstein equations. I mean, if I cannot have vacuum Einstein equations with a stress energy.
Solves the superposition of vacuum solutions of Einstein equations for each configuration that is, like you have a mass in superposition, and each of them is stable in your language.
Okay.
And you believe in quantum mechanics and linearity, you sum up this, it's
Okay.
stable at the end.
Okay, that's possible, I would say. Yeah, I'm not sure, but I see. Yes. So this is for the massless case and the vacuum. You might wonder what happens if I add the mass. That is, I look at the vacuum state of a scalar field which has a mass. Does anyone have an intuition? How would this look like?
Scalar field coupled with linearized gravity. This
Yes. The exact same setup as here. Stress energy tensor of a scalar field who has a mass. And I take that scalar field in its vacuum state. I compute the power spectral density.
increase a little bit.
Increase, right? That's what I would say too. Compute the power spectral density, mass not equal to 0. Turns out for frequencies that are smaller than 2m, which is twice the Compton frequency of the particle, it's 0. If you work out the dimensions, 2m is around 10 to the 24 hertz for a mass of 1 giga-electron volt. It's not just small, it's 0. And that's a kinematical constraint. Basically, it's the mass shell relation of two massive particles. It's a kinematical constraint imposed by just this formula here. You have a stress tensor correlator. And this theta function basically gives you this relationship already. So somehow that's puzzling. There's one interesting fun fact about these, however, is that in this case, the stress energy correlator of a massive field has some analytic structure in the complex plane. So you can analytically continue the stress tensor and the metric correlator to the complex frequency plane. And then using the analytic properties, you can write a version of Cauchy's theorem such that there is this function that satisfies this property. It vanishes below twice the Compton frequency. There is a spectrum, let me call it IR, which is non-zero below the twice the Compton frequency, and there is a large arc at infinity, and the sum of this is 0. So this is just Cauchy's theorem. So here I'm not arguing with the theory. The theory unambiguously says that this is true. The noise is exactly 0 below 2m, twice the Compton frequency. But there's a paper from a couple of years ago by Afshordi, Nelson, and also Kim, where they only evaluate this IR part, and they see a massive enhancement, which satisfies the intuition that you said, that it should be stronger. So that is a non-zero, massively enhanced noise below 0 frequency if you only evaluate this part. But then the theory tells you, if you want to follow the principles, then you are supposed to evaluate only this guy. And this analytic structure is only exposed once you go into the complex plane. So the physical meaning of this relationship is not very clear, but nevertheless it exists.
So we do have massive field in the world.
Sorry?
Like we do have a standard model.
Yes.
Yeah.
And if you do the proper computation, this is the result. This is the result, if you do the proper computation.
Yes, but how about, for instance, if you use the mass term, like the formula on the standard model, then what does it imply for your real operation?
So you want to use...
Below certain cutoff, you should have zero noise from.
So if you use the masses on the standard model, even if for the strongest neutrino mass constraint, which is like 10 to the minus 6 electron volt, I think, even for that, this frequency is just too large for an interferometer frequency scale. So that's kind of the puzzling point. So this is telling us something weird about this observable itself, because this constraint, this is a very, you cannot really argue too much with that. It literally says that this theta function that tells you that once you probe a frequency that is below twice the Compton frequency of a particle, the interferometer is totally unresponsive. Which is somehow like saying, if you have a massive field, then the interferometer is only responsive once the frequency has something to do with the Compton frequency of that particle, which is obviously not a realistic number. So that's 10 to the 24 gigahertz is way above what we measure experimentally. The highest... Of the vacuum of those massive particles. Yes. Yes, yes, yes. So that's a statement about the vacuum. So if no other questions, I have a conclusion slide. Yes? Exactly 0. Exactly 0. That's not an approximation. This? Yes. It's linear, yes. As opposed to 1 over omega L, which is here. And that measures the short distance singularity. Like, there's a simple argument you can have about, you have a metric correlator which is like 1 over x to the some power. And then this large frequency scaling is related to that power. So this is where we are now. I have a conclusion slide here.
Does this mean that it just says that for normal lengths,
For normal,
I mean, the omega is multiplied by L, right?
the omega is?
Multiplied by L.
Yes.
Okay. And omega is just for frequencies below that, right? So that means for larger lengths.
So this bound is on the frequency. You're trying to mix these two statements, right? Like what if it's just, I just need a long interferometer to measure this? No, that's not the statement. This is for the frequency. And for any interferometer with any length, frequency below twice the Compton frequency, the signal is 0. For all L, maybe I could. Yes. Does that? It is confusing. At least I am confused.
Can you say there is no fluctuation at all? I mean, like at this frequency, there is no fluctuation.
From massive fields,
Yeah.
for any frequency that we are currently measuring in an interferometer, as long as you believe that I did the right computation, as in conceptually, that this is connected to the interferometer noise, then from the vacuum of massive fields, there's no effect.
I mean, okay, so if I think about in terms of pi and h bar,
Yes.
and what does it tell me about variances of pi and h bar coming from the mass?
Sorry, what does it tell me about?
If this is 0. Like what?
You're
Because if it is, okay, yeah.
asking what does this tell me about?
Like, I don't know, if this would be a statement about some observables of the, I mean, operators pi and h bar, and I say, okay, fluctuations in one of them is 0, then we say, oh, this
The other
fluctuation
one,
is pi.
the other one could be
Then
infinite.
it will be exposed, so then I would say, okay, then let's measure the other one. This would be, in this language, it would be extremely squeezed.
Ah,
Vacuum, but in this language, it would be.
you're asking maybe this is some kind of squeezing effect, and there's another quadrature to measure, which would be infinite. Ah, I mean, that maybe could be a statement about this. But another thing is that these metric variables, I think they don't satisfy exactly this relationship because these are not canonical fields, right? They are just created by the stress tensor. So the commutation relation of those field variables is controlled by the commutation relation of the scalar field. I don't know the answer to the commutation to that. That's a simple computation. But yes, great question. Okay, any other questions? Because before I try to conclude. Yes.
Can mean, sorry, Thomas, but if you have an interferometer, and it means that at very large frequencies, right, the mirrors do shake, right, with this frequency omega, but it's hard to detect because that's so fast.
At very large frequency.
So basically the length between two masses fluctuates very fast. So it fluctuates with 10 to the 24 hertz, right? And that's hard to resolve.
You could make that
When it's
statement,
slower,
yes.
there's zero.
But then this frequency is not accessible in interferometer. But maybe this could be, or wait.
Yeah, no. At long times, basically, that do not fluctuate. But at short times, like below 10 to
Yes.
24, 10 to 24, it does shake.
Yes. You're making the claim that there is fluctuations above this frequency, except that they are so fast that you cannot resolve them in interferometer. Is that?
Yes.
Yeah,
I'm
yeah.
just trying to.
That's different. That's a more positive way of phrasing the same statement. Yes.
It's about also about fluctuations. So it could be that we have a global fluctuations. They fluctuate such that the
They are.
relativistic goes
They are coherent, yes.
And it could be, of course, local, and then you would see this
Yes.
effect. But any non-local fluctuation that would be global, I guess, will not be captured by that. Am I right?
I had the same intuition. I don't know how to.
Maybe it does fluctuate, but not in the way that it's locally expressible.
Yes. I think this relationship could say something about that, honestly. But that, and yeah, I don't know how to show that, because and then you would have to design an observable which somehow rotates some of these fluctuations into the physical one. I don't know how to do that. But that's an observable design question. That's how it sounds like to me. Like what other measurements could I do that measures the stress energy fluctuations of this field that is not only sensitive to these parts? One idea we had is how much is this affected by having one arm versus two arm? Answer is it's not affected. So this very simple model for interferometer seems to be justified. Same thing is, what if instead of just computing the time delay correlator, I actually consider phase interference? I have an optical field whose phase is given by e to the I some frequency times delta tau as an operator. I interfere the two arms, and what is the intensity that I measure? It's basically related to this guy. So that's also not, it doesn't change. So these basic results from this simple model seem to be quite robust in this framework. Any other thoughts, questions, ideas, critiques?
Yeah, so for non-spin-positive effect, for the two-point function, I remember, I think around 2013, Eugenio and you they calculated the two-point propagator for in-spin mode for graviton. So perhaps that would be a non-preformative effect.
Uh-huh. And do you remember what was the result?
No, I don't.
No.
There is an analytical result, but they didn't do the normalization, so I'm
Uh-huh,
not
uh-huh.
sure how much.
And in spin form, do you get Planck length scaling?
Yes, they will have that. I think they're doing I will try to find the paper. Graviton propagator in spin mode.
Uh-huh, interesting, okay. Okay, that's, yes. Non-perturbative calculation would also be interesting if there are ways to do them. Basically, some outlook and the conclusion. So there are some other interesting papers to consider. First, so basically from the perturbative perspective, I think the most promising direction would be the squeeze state, to compute that, how exactly that looks like from cosmology. There's a paper by Das, Parikh, Wilczek, and Witte, where they're computing these squeezing effects from the cosmological expansion. Also, approaches that are beyond this perturbative quantum gravity, beyond effective field theory. One is by Giovanni Amelino Camelia. There was a recent paper by Gubitosi, Pellecchia, and Pinto, where they consider non-commutative spacetimes. Say there's commutation relation between the coordinates, so that is very different from this setup. There's no geometric fluctuation. There are uncertainties in the coordinates, where this is where the Planck length enters. It is not a normalization, but it's a commutation relationship. And here they are getting that if you just compute geodesic deviation, like there's a geodesic massive object, then its fluctuations are basically enhanced by the IR scale. So you have different power of Planck lengths entering. Similarly, where in the Zurek, they are looking at the effect of causal horizons. So there is an approach motivated by holography. The first paper was in 2019. The idea would be that in holography, the main idea is you have an entanglement entropy not just for a black hole horizon or entropy for a black hole horizon, but also for any subregion which has a causal horizon, let's say a diamond in causal diamond in Minkowski space. Then you have an entanglement entropy which scales with the area of the bifurcate horizon. And then there are degrees of freedom that account for that entanglement entropy. And if they fluctuate, then they could have a different scaling again. Basically, there is an enhancement of the spectrum by L over L Planck, and you again get a different scaling of the power spectrum. So to conclude, I did this little table. If you remember from the very beginning, I postulated that there could be some general scaling of the power spectrum. Let me remove this. With the Planck length, L, frequency, and some joker factor. So now we look through all the examples. So we had the intrinsic fluctuations. These are the TT modes. There's the vacuum state. There was a thermal state. And there was a squeeze state. And there were fluctuations given by stress energy. Let's call it phi. And then let's say another one would be approaches that are beyond the FT. So the Planck-Planck scaling is basically given very simply by which order you are. Planck-Planck squared, squared, squared for all the intrinsic fluctuations, and Planck-Length to the fourth for the backreaction. And if you remember these curves, there are different scalings for the low and the high frequencies. So basically, for the graviton vacuum, you get that for low frequencies, it scales with Planck-Length squared. For large frequencies, there is no scaling with the length. It just goes as 1 over omega, approximately. And basically the same for all other fluctuations. Now the frequency scaling, that was different. So for the vacuum, for low frequency, there's a linear rise. For high frequency, there is a 1 over omega fall off. For the thermal state, that was the main difference. For low frequency, there is a 0. It goes to a constant. So that was an interesting effect. For large frequencies, we go to -1. For squeeze state, we don't know, because it depends on what is the squeezing strength. So here we have the joker functions and beta, and here we have is e to the 2r of omega. And then for the backreaction, the frequency scaling was again different. There was a linear rise for low frequencies and a cubic rise for low frequencies. And then I would say for the beyond EFT approaches, the main point is that they all have linear scaling in the Planck length. And if you work out those numbers, you get some numbers very similar to the actual interferometer noise, except what are the first principle derivations of those noise curves? And I would say that that is a big research gap. Thank you for your attention. Is this always how you?
I'm coming back to my first question. Is that, like, this experiment had hidden many uncertainties, purely theoretical. I mean, like one of them, you would say. So next one is that beam splitter and mirror the quantum object. I mean, if we believe they are quantum objects, they have an uncertainty. Then you have a clock. Your clock should be more precise than what is the interval you want to measure. But if you have a very precise clock, it will be very energetic, so it will backreact. So do you have any idea of which of all these effects will first kick in, so to say? And this is an idealization of all objects being classical, except for the space-time.
The Oh, great question. I would mainly expect, so the question is, do you want to design a model that maybe it's not that crazy and gets close to the noise that we are already measuring? Like do we really want to believe that the noise that we are measuring in an interferometer does have some kind of geometric interpretation? That's question number one. If the answer is yes, then I would expect the effect to be some kind of enhancement with some number of degrees of freedom. Either because somehow the fluctuations that I'm computing here is per particle, and I have a large number of particles in an interferometer, either because the beam splitter and the mirrors are large objects, or photons, a large number of photons, and there's some accumulation coming from there. That's the intuition I have. Yes, I think that's my first order intuition.
So the answer would be there is a good regime in which I can keep all things classical and believe that the noise is coming from the gravitational field.
I wouldn't say you would have to keep the system to be classical for that. I think quantizing the mirrors and the beam splitters would make sense. In fact, the other approaches where you're not computing the time delay of the null ray, but you're looking at the geodesic deviations between the mirror and the beam splitter is exactly a similar approach. You are quantizing them, and you're looking at quantum fluctuations of geodesic distances.
Right, but then since I don't think so, because in the case of the mirror and beam splitter, the time function is not playing any role. I mean, the first order, it should not play.
If you don't allow them to interact gravitationally, yes. If they are just quantum objects sitting.
Sensitivities, I think, in the position from quantum mechanics, so to say, will be much larger than
Yes.
quantum effect.
In fact, that's how we get the current noise, right? That's how we compute the short noise.
Okay, so then my intuition would be that these effects will kick in before you reach the sensitivity of the Planck chain.
No, that's true. Yes, I agree. In fact, yes. So this number, it's not that we don't understand this number. This is short noise. This is already a quantum effect. This is an uncertainty principle. So in that sense, I agree. We measure quantum noise in this interferometer. Is that?
Because imagine you have a classical space-time.
Yes?
Quantum beams play, huh?
The short noise is just a statement about the light, not the matter.
That's right. But then you also have the radiation pressure. That is the mirror effect.
Sorry?
Then you have the radiation pressure.
Yes.
That is the light bouncing the mirror.
Yes, but it's not short noise.
That's true. Yes.
I mean, you know that the level where the quantum state of the mirrors is large enough to do anything, but it's limited by the number of photons. Your short noise interval is limited by the number of photons, not the matter. I think that's what you were wondering about, where the matter is coming.
Yes, yes. I was wondering about that.
I started saying there could be that the uncertainty of the mirror and beam splitter position could surpass the short noise level. Is that?
I'm not sure. Yeah, something like that. Yeah.
I mean, an interferometer,
Like,
in a matter wave interferometer, you have the situation where the position uncertainty is much bigger than the short noise.
Uh-huh. Okay.
But you still detect on short noise because you have pure coherence.
so basically, I think I'm comparing this with the Saliker-Thin phenotype of measurement.
Uh,
You know, that
I'm not familiar with them.
correlations that coming from the relativistic consideration also want to produce black hole and all these things, but it's only about mirror and source and the clock.
Okay.
And I don't know the numbers there, but
And there you have the uncertainty in
you have uncertainty
the mirror position.
the mirror position and the clock uncertainty, because you don't want clock to be so precise to produce a black hole and so on.
Uh-huh, uh-huh, uh-huh. And you're saying that those could be.
I don't. Yeah, I don't.
You're asking.
Yeah, I'm asking just.
Mm-hmm. Yes, I think.
I have a question. What did you say? What is EFT? I didn't get that.
Where? Beyond the FT? Or?
What did you say? I didn't get that.
So these are approaches that are not in perturbative quantum gravity.
So it's a crossed out EFT.
It's beyond, that's what, yes, this is a symbol for beyond the FT. Like
I see, sorry, I didn't get that.
This approach is really going for the linear scaling in the Planck length.
Yeah, I want to ask like whether the some electromagnetic analogous of this is measurable. I would guess the simplest setup could be like a Hanoff-Bohm phase, and there will be quantum fluctuation pickup from the Hanoff-Bohm phase.
Yes.
And whether like can be compared.
Yes, that's one direction I want to go to, at least to explore what is the electromagnetic picture of this setup, and what if I add the gravitational field. I expect the numbers to be small again in that case.
Yeah.
The physical picture would be that you have photons in an interferometer that you allow to interact gravitationally. And is there some kind of accumulation effect once you allow the cavity to evolve on its own?
And also allow you to explore different interesting state to see.
That's right. That's right.
And I would guess one need to measure electromagnetic first before the.
Yes, and in fact, if I do that computation, I'm definitely going to get this number because it's a short noise, and that is included in the model. And then I can ask, once I have the gravitational field turned on, what are the deviations from this? Is there some kind of non-Gaussianity I can derive? Or more like, what is the scale of that non-Gaussianity? And is there a way to engineer that to be observable? Sorry, what gravitational waves? Primordial gravitational waves. I think, yes, that's a similar idea, yes.
Because, I mean, in gravitational wave detectors, they do publish papers about bounding primordial.
That's right. There are two effects. One, it would be the primordial gravitational waves. The other they are looking for is whether if you consider the current gravitational waves we are observing, which are black hole mergers, neutron star mergers, then what are the quantum deviations to those? You also get squeezing effect. You recompute the binary black hole merging. You get the gravitational wave produced from those. If you do the quantum computation, you get deviations from the classical solutions in terms of squeezing, and that's another thing you can bound from the interferometer measurements. But those are gravitational wave measurements, which are like isolated events. Here we are talking about constant noise.
Yeah, no, I think this paper's about this early gravitational waves is about just background noise, basically.
Yes, yeah, that's another way, yes.
Yeah. But I guess they're far away from this, I mean...
Closer than...
I mean, there must be some reasonable estimates for the squeezing strength, right? I mean, people claim inflation theory is all that great, right? So, I mean, this should be known to a high precision.
That's right. Inflation would scale this up. So that's inflation would scale this up.
No, but I mean, inflation would tell you exactly what this is, not?
Yes.
So it's not unknown, because you made a question mark there.
So the one paper, I'm not familiar with the full literature. One paper I know is this one, where they actually compute the squeezing. But in the end, they don't plug into these numbers, so they don't have a conclusion about whether this is observable or not. So there are computations on that. The ones I'm familiar with, they don't make the conclusion, so I don't know it myself. That's why they're not finished yet, I would say, yes.
But I mean, in principle, cosmology or inflation theory is very well defined, right?
Yes, in principle, this is computable. Yes.
Imagine that you would prove not only fluctuation of space-time, but also inflation.
So along these lines, like, is the squeezing in the correct direction for inflation? Because intuitively, I would think it works against you because it's bringing the gravitons further away in a sense.
Uh-huh.
And so the squeezing would make the effect smaller in my intuition. Do you know if it's the correct sign?
The squeezing would make the effect smaller.
For inflation, I mean.
No, I think that should be positive. Why? This measures the expansion rate of the universe. So as the universe expands, it squeezes.
So as the universe expands, R is larger than 1.
Yes.
If I
Or you could say that you have high energy quantum fluctuations in the early universe, and inflation pushes them into the low frequency where you don't have a.
Probably,
That's another.
but if you think the inflation is extension, which might be wrong, but in your head it's extension in space, then this width in space, which is precision, like you have a meter, will expand.
Yes.
And then you have a feeling that now you have a less precise meter.
Yes.
Because the units is larger then. Like autonomic precision is larger.
Mm-hmm.
Uncertainty
But
level
isn't
is
less
larger.
precision more noise? Isn't that what you? I mean, here you claim the noise is bigger.
Yes. Yes. Yes.
Uh-huh.
Question is at what frequency? I think that effect you're talking about is that this function has supported very low frequency, which is not the same as how large is the squeezing effect. But I don't know the result, so I'm not claiming it's.
I'm just trying to explain why it's counterintuitive.
Uh-huh, uh-huh.
But I mean, somebody must have done this calculation, right? So I mean, if the two papers about Brownian fluctuation.
No, there definitely are. Yes, yes, yes. Whether it's precisely this computation or.
He sounds about. I mean, inflation is
Sorry.
into the 60, right? Something like that. So I mean, you get this huge, these many orders of magnitude. I mean, there are factors that large, basically.
Yes, yes.
Okay, any more questions? If not, thanks, Robin, for the very nice talk.
Yeah, thank you. Thank you.
Okay, let's now stop the recording.
Recording, okay.
And you can tell us about.
So do I?